All right. Okay, so before we start today, can you guys hear me? Yes?
Yes.
Okay. So over the last couple of days, there was some questions about problem 5 in particular in the homework. And so I've added a lot of clarifications. Yeah, I agree that differential notation, because it's a set, creates problems, and yeah, but it's the way it's written in all the textbooks and so on. So it's better to make it clear exactly what you're trying to show rather than using the differential notation. Just talk about subgradients, and then it'll be easier. So I've rewritten all the problem statements so that it's clear what you need to show. So for example, for scaling, what I want you to show is that G is a subgradient of F at some point X, if and only if AG is a subgradient of AF. Now, for this particular statement, going both ways is actually very easy. Once you prove the implication going one way, then the argument can easily be reversed. So the implications go both ways very easily in this. Now, in the second one, I only ask you to take the implication one way. In other words, I ask you to say that if I have two functions, f1 and f2, and g1 is a subgradient of f1, and g2 is a subgradient of f2, then the sum of these subgradients is a subgradient of f1 and f2 at that point x. So technically, you should be able to go the other way as well, but that's a little trickier to think about, because what you need to go the other way, you need to show that the only way I can create a subgradient for the sum is by using subgradients of the individual functions. So establishing that fact is actually a little more technical. I don't really want you to do that. And in fact, most applications, when we're dealing with subgradients, you don't care if you found all the subgradients of a function, okay? As we see in the subgradient descent algorithm, and which we're going to talk more about today, as long as we found one candidate or a few good candidates for the subgradient, we can use them in the algorithm. So identifying all of them is not necessarily that important practice anyway. And the third one, this was actually the way this is typically worded in textbooks, and I just picked these problems out of textbook, is that it's not completely accurate, I guess, the wording. So that's why I clarified this problem a little bit more. So for example, here H is f of ax plus b. Assume for simplicity that A is a square invertible matrix. If A is not a square matrix, things get a little more messy, and you can think about that on your own if you like. But for example, A can be a non-square matrix, but you need to go from the original space, maybe n-dimensional space where X sits, to an m-dimensional space that's smaller. Otherwise, this result will not hold. Okay, and so I just assume that basically you're transforming X to something else that still remains in the same dimension. It makes things easier, and we'll assume that A is invertible. And what we need to show in this problem, what I want you to show, is that if G is a subgradient of F at the point AX plus B, if and only if A transpose G is a subgradient of H at X. Okay, so that's what I want you to show. And again, this is the implication can easily be shown to go both ways here. So that's why I put the if and only if here. All right. So any other questions about the homework? There was also actually a question about problem 7 about whether d lambda is always differentiable, but it doesn't have to be. And one reason why it may not be differentiable is because x of lambda need not be unique. So the solution to this optimization problem is not unique. In fact, you can show that minus h of x of lambda is a candidate for a subgradient, but there could be multiple solutions. So there could be multiple candidates for a subgradient, which means that the gradient of d at some lambda may not exist. Okay, and it's actually very easy to show that minus h of x of lambda is subgradient for this minus of d lambda. It's much easier than the proof that we did in class when we assumed that d lambda was differentiable. Okay. All right, so that's all I want to say about the homework. Any questions? Or did I confuse you more?
Why do we have A is invertible?
Hold on one second. I couldn't hear what you said. Repeat.
Yeah, I just want why is the problem C? We need that A is invertible. Why do we need that?
Why do you need A is invertible? Because you're going to use a statement like f of y is bigger than f of x plus something, right? So so f of and so you need to be able to go from y to ay, and should be a one-to-one mapping between y and ay. Okay. Otherwise, a statement that holds for all y you may not hold for all ay plus b. So that's why you need that invertibility condition. And if it's not a square matrix, then you need it to be an m by n matrix where m is less than or equal to n, and it has to be full rank. That means it has to have rank m. So you can actually show the statement for non-square matrices, but it is much easier when it's square, so that you're not actually going to a new dimension. Otherwise, if you think about it, x might be in n-dimensional space, then this function f is really being defined in possibly a lower dimensional space, m less than n. Okay, and so is h. So it's a little bit confusing because you're mapping this x. H is defined on x, but this function is really defined in a lower dimensional space. So okay, when you write down the steps of the proof, you have to be careful about that. So so that you don't have to worry about it, I assume that A is a square matrix so that you're not changing dimensions. And I assume it's invertible so that you can make statements going both directions easily. Okay. Does it make sense? Once you start writing down the 2 or 3 lines that it takes to prove this, you'll see why you need invertibility. Okay.
Yeah, thanks.
All right, so let's again briefly review what we did last class. So we're talking about subgradient methods. And I think it was, who was it who pointed out about going both ways? So I think it might have been Talha who pointed this out in the last class. So in the examples that we did. So let's actually spend some time about that, on those examples, I mean. And I added some clarifications for all these examples. Okay, so basically, if you want to make sure you have identified all the subgradients in this example, you know that any g between -1 and 1 is a subgradient. But how do you make sure that something that's outside is not a subgradient? And for that, that's why I added this note here. So if g is bigger than 1, then this fails to hold for y positive. And if g is less, I kind of mentioned this in words last time, but I actually wrote it down in the notes now. So in the post-class notes, you'll see this clarification. So by adding that note, we're basically saying that anything outside this set -1, 1 cannot be a subgradient. Okay. The same. So then this statement is accurate. Then the subdifferential is exactly the set. It cannot be anything outside that set. Right? That makes sense. Now, the other example that we did, the same thing. This example, Okay, we identified subgradients at this point. Everywhere else, the gradient exists. But then we started doing this, but just to make sure that the subgradients are only the points between 0 and 1, you can easily check that if G was less than 0, then this condition will not hold. Okay, and similarly here, if G is bigger than 1, this condition does not hold. So the only candidates for subgradient are between 0 and 1 for this example at point 2. Okay, and similarly you can do this for point -2. So you really need to add these conditions to make the statement this statement here about the subdifferential completely accurate mathematically. Okay, and most if you look at examples in textbooks, they don't really pay much attention to that, really. But okay, so because this condition for a subdifferential has to hold for all y, right? So if it doesn't hold for some y, then it cannot be a subdifferential or a subgradient. Okay, so that's a small clarification there that I added to these notes. And then we were talking about the subgradient descent algorithm. Now, today's lecture, I'm going to spend some more time on this. But in particular, I mentioned last time that even though we call this subgradient descent, this G direction, the subgradient direction, may not be a descent direction in general. Okay, but still the algorithm works. Okay, so we'll say more about that in today's lecture. Any other questions about last time? Okay, I'm going to start by doing 2 more examples just to make it clear how we find subgradients, because that's the most important part of the subgradient algorithms. How do you identify subgradients easily, and then you can use them in the algorithms, right? Okay, so first let's look at a commonly used function that's this the norm. So a lot of times the norm, L2 norm, or sometimes a norm squared is used, but if you use a norm as what's called a regularizer, okay, to an optimization problem, then the norm actually is not differentiable at all points. Okay, and in homework problem number 6, actually we're looking at the special case of an L1 norm, where you take the sum of the magnitude of x1 plus x2, and they're also at the point when one of those coordinates is 0, then any one of the coordinates is 0 in an L1 norm. You're not going to have derivatives exist, right? A gradient doesn't exist. So you have to really go for subgradients in that case. All right, so but let's look at this this problem. This f is a convex function. Okay, we're using the Euclidean norm, square root of x transpose x. F is convex, and why is f convex? Anyone?
It's a square root of the sum of convex functions.
Not quite. We actually talked about this like a long time ago, maybe in lecture 3 or something like that. It's the triangle inequality, right? So you just take convex combination, apply the triangle inequality of norm, and you automatically get convexity, right? If you don't remember this, go back and make sure you can check that this is it's one line, but I just want to make sure that you can go back and see that yourself. Okay, so this is a convex function, so we can define subgradients even at points where the gradient doesn't exist. But if you look at x not equal to 0, the gradient exists. For all x not equal to 0, gradient exists. Okay, some of the components may be 0, but as long as the entire vector is non-zero, the gradient exists. Okay, and what is it equal to? I mean, you just take the derivative, right? So in this case, the differential is the same. Sub-differential is the same as the gradient because the gradient exists. It's 1 over 2 squared this times 2x, right? And this is equal to x divided by the norm of x. The 2's cancel. So that's the gradient when x is not equal to the 0 vector. If x is the 0 vector, then of course you can't divide by 0 there. So that's one reason why the gradient does not exist. Okay, but then you might have a subgradient at 0. So what's a subgradient at 0?
Is it 0?
So let's think about it. So at 0, you can go in. You could. There are a lot of directions that are possible, right? That'll still keep the function above. So the intuition says that all directions are okay, except that you want to make sure that the norm of the thing is less than 1. Norm of the subgradient is less than 1. If it's bigger than 1, then the line, you don't expect that linear boundary to stay below the curve. So that's the intuition, but we can verify this mathematically. So what we really need to show here is that for any g such that the norm of g is less than 1, okay, that fy, which is the norm of y, is lower bounded by f at 0 plus, this is just a definition, right? It's a definition of for all y belonging to Rn. You need to show this for all y. So let's call this equation 1. Okay, but the f of 0 is 0. So okay, this is 0. And so this is just, all you have to verify is that G transpose Y is less than the norm of Y. So what do you think you can use to show this? You have an inner product, and it's trying to show that it's
Cauchy-Schwarz.
Cauchy-Schwarz, very good. So, so this is less than the norm of G times the norm of Y, which will be less than the norm of Y if the norm of G is less than 1. Okay, for all Y. So if G is less than 1, then the condition holds. And so we have verified now that any G that has norm less than 1 is a valid subgradient for this function at the point 0. Now, to satisfy Talha, who asked this question last time, if you want to establish a converse, you need to show that if G is something that has norm bigger than 1, then the condition is violated. So let's see why that's true. Okay. So suppose G has norm bigger than 1. Okay. So now I just need to find one value of Y for which the condition is violated, and then I'm done. Then I've shown that that cannot be a subgradient. Because this subgradient condition has to hold for all Y belonging to Rn. So even if I find one Y for which this doesn't hold, then it's not a subgradient. Okay, So I'm going to try and judiciously find that y, and that, let's try this. You have to think about it for a minute to see why this works, but let's take y equal to just the normalized version of g. Okay, so basically g has norm bigger than 1, so I normalize it so that now my y actually has norm 1. So y has norm 1 because I've normalized g by its norm. But then if you look at g transpose y, that's equal to what? G transpose y is g transpose g divided by the norm of g, which is equal to the norm of g, because g transpose g is norm of g squared, and that's bigger than 1. So here I've shown that the left-hand side is equal to 1, but the right-hand side is bigger than 1. So this equation 1 does not hold. Right? So the only candidates for the subgradient are direction g, for which the norm of g is less than or equal to 1 at the point 0. Okay, is this clear?
I have a question. So why we need to establish the converse part? I mean, why?
Oh, yeah. So when we make the claim that the subgradients at 0 is exactly this set, then we need to make sure that anything that's outside this set cannot be a subgradient. And that's why we need the converse.
Okay.
Yeah, a lot of textbooks would ignore this part of the argument, but I think to be mathematically correct, you really need this. And it's usually not that hard to show in most examples. You just have to find a good candidate for y. It's a little bit of guesswork, but let's do another example. This is a two-dimensional example that's slightly different from, it's a little harder than the one that you have in your homework. Okay, so this is x1 minus x2. Okay, so we have a two-dimensional function in 2 dimensions, and it's this, airplane wing function, like this v function here. Okay, it's clearly convex, and you can easily establish that using the triangle inequality if you want to. Okay, so show that at home if you're not convinced. But the picture clearly indicates that it's a convex function. Right? So what happens in this function? So if x1 is bigger than x2, then the norm of x1 minus x2 is x1 minus x2, and the gradient exists in this case. And then what is the gradient equal to?
1, -1.
1, -1. Okay. Similarly, if x1 is less than x2, x1 minus x2 is x2 minus x1, and here also the gradient exists, and it equals -1, 1. Okay. So basically, as long as x1 is not equal to x2, the gradient exists. So then what happens if x1 equal to x2? What do you think the gradient will look like in this case? Or subgradient, rather. So if x1 equal to x2, you can see that here. This is the line x1 equal to x2. And you can see that the gradient doesn't exist here. But what property does a subgradient might have? So subgradients go all the way from this to this, right? Okay. So how do you write that down? So the guess is that it's going to have the form, it's going to have some form AB always, right? But from looking at the gradients for x bigger than x1 bigger than x2 and x1 less than x2, you can guess that A should be equal to minus B, or A plus B equal to 0. And the other thing is that if you look at the direction here, okay, so you can go all the way to a 45-degree line, right? And when you fix x2, for example, and go along x1. So I think so that gives you the idea that you can't go beyond 1 and the slope of 1 in either direction. So that means that your guess would be that the norm of A should be, or the absolute value of A should be, and B, of course, because B is just negative of A, should be less than 1. Okay, so this is a good guess for the subgradient. And let's see if we can show that it is the answer. Okay, and here in this example, it takes a little harder. It takes a little more work. It's a little harder to show the converse, to show that anything outside the set is not a subgradient. But we'll do that too, just to be complete. So if x1 is equal to x2, say that the x1 is equal to x2 equal to some constant c. Right? Right. Just assume it's some c. C could be positive or negative, or even 0. Okay, what we need to show is that the absolute value of y1 minus y2 should be bigger than f of 0, which is 0, of course, in this case example, plus, now my subgradient is AB. So AB transpose will give me a row vector with AB times y1 minus x1, which is C, and y2 minus x2, which is also C. And this has to hold for all y belonging to R2. So everyone see that this is the condition we need to show? Okay, so let's rewrite this, the right-hand side here. And so the right-hand side, this is 0, so I don't have to worry about that. Then I have A, y1, plus B, y2. And then the constant is just C times A plus B. So I need to show this for all y belonging to R2. But if A equals minus B, then A plus B is 0, so this goes away. If the norm of A is less than 1, then so A is minus B, so this is A times y1 minus y2. And A times y1 minus y2, if A is less than 1 in magnitude, has to be less than the absolute difference between y1 and y2. So this holds, basically. So this has to be bigger than A times y1 minus y2. So this means that this equation holds. Let's call that equation, let's call it 2. So the equation we need to check holds. So we have verified that everything inside the set is indeed a subgradient for the point, for a point x1 equal to x2. Okay. No matter what x1 and x2, what values x1 and x2 take, it doesn't matter what they take. Okay, this is always okay. And it's not hard to see from this picture. No matter where you are on this line, the subgradients are all basically the same. Okay. So need to show the converse now. To show the converse, there are two things that we need to look at. One is, let's say A is not equal to minus B. So two things can happen for the converse. Either A is not equal to minus B, or the norm of A is bigger than 1, or both could happen. Right? And I have to make sure in all those situations, I'm not going to be able to satisfy the subgradient condition. So let's go ahead and show that. I'm going to go over this a little quickly, and because again, it's a little bit beside the point in some cases, because I kept saying earlier that as long as you can find a good set of subgradients, you're happy. You're not you don't really need to find all of them necessarily in practice, but let's go ahead and, at least in this example, since it's easy, relatively easy, just go ahead and do it.
Can I ask a question from the previous page?
Mm-hmm. Yeah.
I got confused when you say f of 0. Shouldn't it be like f of cc or f of...
Oh, sorry, it's not be f of 0. Yeah, very good point. So it should be f of cc.
Thanks.
Very good. Or f of x1, x2. Yeah. Sorry. Okay, so to show the converse, suppose a is not equal to minus b first. Okay. All right. Then if I look at c of a plus b, this is the same as saying a plus b is not equal to 0. So c times a plus b can either be positive or negative depending on the sign that a plus b has. All right, and the sign that c has. So let's look at the case where c times a plus b is positive. Or let's actually. Okay. Let's look at the negative first. Then setting y1 minus y2 equal to 0. Actually, so c could be 0 in this case. In that case, this could be 0. So you can treat c equal to 0 separately as well. So that's probably one case that I haven't covered in this, but it's not that hard to do. Okay, so setting y1 equal to y2 equal to 0 gives us that y1 minus y2 is 0. But if we look at a y1 plus b y2 minus cab, well, we have that y1 equal to y2. So I got y1. Oh yeah, so both the y's are 0. So okay, that's what I was trying to get at here. Okay, so I've set both of these y's to 0 in this case, and then I get that. I get that this part will be 0, and I'll just get minus c times ab, which is positive. C times a plus b, positive. Okay, so but that means 2 fails to hold. Yeah, so if c is 0, then you can make y1 equal to y2. You have to choose the sign of y1 and y2, make them equal, and choose a sign so that a plus b times that constant is positive, and then again you'll get the same conclusion that y1 minus y2 is equal to 0. So you can easily cover the case when c is 0 separately. Okay, so I didn't do that here, but you can do that. So, but what if c times a plus b is positive? Okay, then you can set y1 equal to y2. You just have to find one choice. There are many choices, but just one choice is good enough. It is equal to 2c, and then in this case also the absolute value of y1 minus y2 is 0, but the right-hand side, a y1 plus b y2 minus cab is equal to c times a plus b, which is positive. So again, 2 fails to hold. Okay, and you can similarly cover the case. I should probably write that down. So 2 fails to hold if c times a plus b is equal to 0. Okay, so that you can do that at home. So finally, what happens if actually a plus b is equal to 0, but the norm of a is bigger than 1? Okay. Here again, you can easily verify that if A was bigger than 1, absolute value of A is bigger than 1. If A is actually bigger than 1, then setting y1 equal to y2 plus 1 makes 2 fail. That's easy for you to go check. And if A is less than -1, setting y1 equal to y2 minus 1 makes 2 fail. Okay, so basically, when you're outside the set, the set, of vectors of the form 8 times 1 minus 1 with the absolute value of A is less than 1, then it cannot be a subgradient at x1 equal to x2. Okay, so these are the only subgradients when x1 equal to x2. When x1 is not equal to x2, gradients exist and equal to that. Okay. Any questions? Yeah, so doing this, verifying the converse usually takes a little more work than actually just establishing that something is a subgradient. That's one of the reasons why I changed the wording of the last question as well in your homework 5. And I just said, show that every solution is a subgradient. As long as you have good candidates for subgradient, you can apply a subgradient algorithm to find the optimum.
Can I have a questions?
What's that?
Can I have a questions? So for the homework problem 5, some of them we need to show in both directions. So is it the same as what we are doing right here? Like,
no, that's actually even much easier there, because you just show the implication, just from, it's more of a definition kind of thing. Okay, if something is a subgradient, then that's if and only if the subgradient condition holds. That's a definition, right? And then you can keep going if and only if all the way through. So once you prove the implication one way, it goes the other way as well in those two cases. That's why I asked you to do that in these examples. In this one and this one, the implication, basically once you prove the forward implication, the reverse just follows automatically. Okay, that doesn't happen with this one. That's why I didn't ask you to do the reverse implication on that one. Okay, and same with here. It's basically it's much easier to show that these are subgradients of B lambda, but showing that those are the only subgradients of B lambda is a little more difficult. Okay, so subtle point, but which usually doesn't matter so much in practice, but yeah, it's still a point to consider. Okay, so one last thing before we take a break. Okay, so a subgradient is not necessarily a descent direction, or the negative of a subgradient rather is not necessarily a descent direction. So let's actually see what that means. So maybe that goes back to maybe even lecture 5. Okay, so if you remember when we started talking about gradient descent in lecture 5, okay, we said that any direction that has any decay that has it's going along the negative, has a positive projection along the negative gradient is a descent direction. What does it mean when we say something is a descent direction? What we mean is that as long as we go in that direction by a small amount, we're guaranteed that we'll decrease the function. Okay, if you go by a large amount, for example, here, if you go by a small amount, you're decreasing the function. If you go by a large amount, you may end up here, which is not a smaller value, but it's a descent direction in the sense that if you go by a small amount, you are guaranteed that you will decrease the function. And that's why you can use adaptive rules like Armyho's rule, okay, which allows you to slowly change the step size so that you're still guaranteeing that you're decreasing the function and not going to in the other direction and increasing it, right? So you can do things like Armyhost rule, adaptive, or other things like optimal line search. All these things make sense when the decay is a descent direction. Okay. But if you go to this one, if you go to negative gk, and so starting at xk, you subtract out alpha times gk, this actually may not be a descent direction. What that means is that this may be greater than f of xk for all alpha positive. So no matter how small you make alpha, you may not be able to decrease the function for some gk. That could happen because gk is not really a gradient. If it was a gradient, it couldn't happen. Again, going back to lecture 5, why can't that happen with a gradient? So if you look at what's happening with the gradient, is that if you look at a first order expansion, you can expand out alpha xk plus alpha dk as f of xk plus this term, right? This term is going to be negative as long as dk is a gradient direction. In particular, if dk is the negative of the gradient, then this is just the norm squared, negative norm squared of the gradient, so it's a negative value. Okay, plus little o of alpha. So that means that if I take a small step, this little o alpha can be ignored, and I'm always going to decrease my function relative to f of xk. But if this was not a descent direction, then I couldn't have said that. Right? So that's what's happening here. So this G may not be a descent direction. Okay, and we'll see an after the break. We'll see an example of that. Okay, an example of a function with computed subgradient and show that there are some subgradient directions that are not descent directions. Okay, so when we talk about subgradient descent algorithm, you have to be careful. That's why I put quotes around it. It may not be a descent direction, but it still works. Okay, and we'll show how we can make these subgradient methods actually work and converge to the optimal solution in practice by a careful choice of step size. But it's not going to be Armyhost rule anymore. It'll be something else. Okay. All right, so let's take a short break and then we'll come back and talk about that. All right. All right. Any questions before we proceed to the example? I guess to maybe further clarify what the question of here. So about this thing about the if and only if here. So when you say that something is claim that G is a subgradient of f at x, okay, the definition for that says that f of y should be bigger than f of x plus G transpose y minus x, right? But that's definition. When you have a definition, that implication goes both ways. So G is a subgradient of f at x if and only if, okay? So this statement is if and only if f of y is bigger than f of x plus G transpose y minus x. Okay, so then from there you can proceed if and only if throughout. Okay, definitions are always if and only if statements. Okay, so let's get to this example. So let's look at this example. So here I've cooked this up so that x1 I have an absolute value here, but x2 is with the square. So things that the x2 part behaves nicely, is differentiable, but the x1 component has this absolute value. Okay, so it's easy to show. You can verify this at home if you like, that that basically subgradients will exist except so gradients will exist except when the x1 component is 0. Okay, and in particular, so let's say that we were at a point xk in our iterations gradient in our subgradient method, where xk was the 0.01. And at the 0.01, it's not hard to see that the set of subgradients is given by the set. So the first component, x1 component, has an entire set of possibilities, -1 to 1. And the second one, with this gradient respect to the second one exists. So you get that it's just 1 here. So it will just be x2, which is 1. So this is 1. Okay, and see that? So now let's consider one of these. So suppose I say, okay, I'm starting at this point xk. I need to find a subgradient direction to go on. And let's say I chose this, once I know these subgradients, I'm probably not going to choose that. But suppose I, in high dimensions, you may not know exactly what is a good subgradient and what's not. In this example, you can easily see that -1, 1 is probably not a good direction to go. Okay, but we'll see why it's not a good direction. All this example is trying to illustrate is that there are some subgradients that are not going to be descent directions. So let's take gk equal to -1. This belongs to this subgradient set. So this could easily have been what I chose when I was at xk equal to 0, 1. Now let's see what happens to f at xk minus alpha times gk, where alpha is something positive, right? So this is the same as f at 0 plus alpha and 1 minus alpha, the second component. Okay, and by definition of f, it's just alpha plus half 1 minus alpha squared. Alpha is positive, so the absolute value of alpha is the same as alpha. Right, so this is alpha plus half 1 minus 2 alpha plus alpha squared. And you see here that the alpha cancels, the linear term cancels, and all I'm left with is half 1 plus alpha squared. So alpha is some positive number. Alpha squared is something also positive. So this is bigger than half, which is equal to f of xk for all alpha positive. So no matter how small I make my alpha, I'm not decreasing the value of my function. So this particular subgradient direction or negative of that is not a descent direction. So no matter what you do, to your alpha, try to do Armyhole's rule, anything, nothing is going to work, because no matter how small you choose your alpha, it's not going to make the function become smaller. But that doesn't mean you shouldn't use it. Okay, so it turns out it's okay as long as you don't make the bad choice all the time, essentially. And you won't be making a bad choice all the time. Well, that's the point. As you move around, you're going to change your xk's, and then the set of subgrades is going to change there, and so on. And so you're going to be okay. For a convex function, you're going to be okay eventually, and you can get to the minimum. Okay. So, and this is true that actually, if f is convex, there is some gk in the set of subgradients for which minus gk is the descent direction at any point xk. Okay, and it's not hard to check, for example, in this example, that 1, 1 is a descent direction. Minus 1, 1 is not, but 1, 1 is a descent direction. Okay, so, but then so maybe you can say, well, I can modify my algorithm to always choose gk so that it's a descent direction. But it may not be easy to do, especially in high dimensional settings. Okay, even if you know the function is convex, like in a neural network with millions of elements, right? So this may be difficult to do. Okay, so this means that you really can't use backtracking algorithms for adapting the step size. So should we give up or do something else? We saw last class that even if you use a fixed step size, right? As long as this G is bounded by some A, okay, you can get awfully close to the optimum solution, the minimum of the convex function. There's some error term that can be made small by choosing your alpha to, making it smaller, right? So it's possible. You're not going to get exactly to f star in the limit, but you can get close, right? And the idea there was to, rather than just keeping only the previous value of the optimum point, you look at the minimum over the entire history and keep track of that. As long as you keep track of that, then even though gk may not be a descent direction, and some negative gk may not be a descent direction at some time steps, you're still okay, because this f of the best value that you found, this is sometimes called xn best. So the best value you found up to time n will still get pretty close to f star. Okay, what we're going to show now is that we can not just make it close to f star, but we can actually make it equal to f star in the limit by choosing the step size properly. Not adaptively, this is going to be done beforehand. We're going to choose the step size sequence beforehand, and that will guarantee that we converge to f star. So let's see how we do that. Okay, so again, we'll make the same assumptions like we made in the last class. Okay, I'm not going to repeat that. F is convex, the minimum exists, and the subgradients are bounded everywhere. Now, instead of using a constant step size, the big difference will be that we're going to use a step size that's varying, right? So we're going to use a step size that's alpha k instead of just alpha. So let's do the analysis like we did last time with alpha replaced by alpha k. So most of the steps from last time actually go through up to a certain point, and then we'll have to figure out what to do. Okay, so let's see that. So these steps are identical to what we did last time. So xk plus 1 minus x star is this, as alpha k now gk minus x star. Expand the square out, you get this. The same terms as we had last time, except we have alpha k here instead of just alpha. And then we upper bound the subgradient by a squared, so we get that. And then how do you deal with this in a product? You use the definition of the subgradient. So again, same step as last time. And so you get to this point here. Okay. And what we did last time when alpha was fixed was we used, we replaced this by the x and star and used the telescopic sum to bound this difference. We can't do that anymore because the alpha is now allowed to vary with k. So this is where we will diverge from last time's proof. Okay. All right. So what do we do now instead? Let's actually write one more step of this iteration on the right-hand side. So just like I could write xk plus 1 in terms of xk like this, I can write xk in terms of xk minus 1 in a similar manner. So let's go ahead and do that. So this is xk minus 1 minus x star squared plus alpha k squared a squared plus alpha k minus 1 squared a squared plus 2 alpha k f star minus f of xk plus 2 alpha k minus 1 f star minus f of xk minus 1. So I've gone through one more iteration on the right-hand side, and I get that expression. Now you can see that I could keep doing this until I get all the way to x0. Then I'll have a sum of terms like this and a sum of terms like this on the right-hand side. So let's do that. But rather than iterating from k plus 1, let's go from, say, n here and see what happens on the right-hand side then. So that's what we'll do in this. So let's iterate from n going down all the way to 0. So if we did that, you get xn minus x star squared is x0 minus x star squared. This will start to look a little bit like what we had last time. But then instead, on the right-hand side, we'll have a squared times the summation from k equal to 0 to n minus 1 alpha k squared. So that's like terms of this form. So a squared times the sum of the alpha k squareds. And then I'll have 2 times the summation k equal to 0 to n minus 1 alpha k times f star minus f of xk. Okay. So I have a sum now on the right-hand side. Okay. So now, again, like we did last time, let's define f of xn star as the best value that we have found from the past. So time n, capital N, the best value that we have found, the minimum. It's the the value of x that xn star is the value of x that results in the smallest value of f from the past. Okay, again, by the way, this smallest value can easily be computed recursively, so you can update it, and every timestamp you just update the smallest value, right? That's easy to do. So you can, it doesn't really take. You don't have to store all the f values from the past. You can just keep the smallest value and compare it to the current one and update it a bit smaller. Right? All right, so we have this plus same term here, k equals 0 to, not bother writing all this down. Now, what I'm going to have is 2 times summation k equals 0 n minus 1 times alpha k. I can take that outside, and then I'm left with f star minus the minimum value xn star. Okay, so now let's take this stuff to the left-hand side. Let's take this stuff to the left-hand side and divide by this coefficient here. Okay, so I get this is x0 minus x star squared minus xn minus x star squared plus a squared times summation k equals 0 to n minus 1 alpha k squared divided by the summation of 2 times the summation, I guess, of alpha k. Okay. Now, but again, this term is negative, so I can remove it and still get an upper bound. So I'll remove that. So all I'll be left with is x0 minus x star squared plus a squared. Okay. And in particular, if I had a constant step size, right, then I would get back the expression that I had last time, which is a squared alpha just a squared alpha divided by 2, which is what I had last time. Okay, but now what we want to do is see if we can, but then that would leave an error term, right, if I use a constant step size. But I want this thing to shrink to 0. Okay, so f of x n star minus f star is always going to be positive, right, non-negative, because f star is the minimum. So this is always going to hold. So as long as I can show that this guy can be made to go to 0 as n goes to infinity, I've sandwiched this together, so I get that I've reached f star. All right, so what do I do? So here's an option. Suppose I can choose my alpha k in a diminishing manner. That's why it's called diminishing step size, such that the ratio of this guy to this guy goes to 0 as n goes to infinity. Suppose I could do that, right? So this limit is 0. Then it's clear that this right-hand side becomes 0, right? Right? Because this is just a constant. I'm adding this thing here, and this divided by this is going to 0. This divided by this is always going to go to 0, because for this limit to go to 0, this summation has to go to infinity. So for something like this to hold, I need the sum of the alpha k's to diverge, right? And the sum of the alpha k squareds to be in such, it could diverge, but it has to go in such a manner that the ratio goes to 0. If that happens, then the limit as n goes to infinity of f of xn star will equal f star. No gap. Okay. So let's take some special cases where we might be able to do something like this. So first special case, and we'll also get the corresponding convergence rates. Suppose we take alpha k equal 1 over k plus 1. For k equals 0, 1, and so on and so forth. Right? So the summation of alpha k from 0 to n minus 1 is equal to the summation k equal to 0 to n minus 1 of 1 over k plus 1, which is the same as the summation from k equal to 1 to n of 1 over k. Anyone know what this diverges to infinity, but do you know what it goes to infinity as? At what rate? Anyone? This is like 1 over x. Yeah? Go ahead.
It's slow.
It's slow, but what is the rate? When you integrate 1 over x, what do you get?
Log of x?
Log of x. So this is actually goes as log of n. And you can actually prove that it goes as log of n by using the Riemann sum, right? So the Riemann approximation or the Riemann bound on the integral. So this actually can show that this is greater than log n. So it diverges to infinity faster than log n. Actually, it's also less than log n plus 1. So it diverges to infinity exactly at the rate log n. Okay, what about alpha k squared? In this case, alpha k squared I made the sum go from 1 to n, so it'll be just 1 to n, 1 over k squared. And anyone know what this one goes to? Is it divergent or convergent?
Convergent.
Convergent. So it is actually convergent, something finite. As n goes to infinity, it actually goes to pi squared divided by 6. It doesn't matter what that constant is. The fact that it converges is what's important. So if we go back and look at this expression, so here what's happening is that this guy is going to a constant and then goes to infinity. This guy is blowing up as log n. So the ratio is going to 0. So the difference between f of xn star and f star is of the order of 1 over log n. So it's going to 0 as 1 over log n, which is slow. Anyone remember what the rate was for convex, not strongly convex, but just convex functions? What's the rate of convergence of gradient descent?
Log n.
No, gradient descent. Gradient descent just so this is log n, but what is gradient descent without strong convexity? Anyone remember?
1 over n.
1 over n. Yeah, so that was lecture 7. Remember? Rate of convergence is 1 over n. If you don't make strong convexity assumptions, you don't get linear convergence. You just get 1 over n convergence. By linear convergence, we mean that geometric convergence, right? So this one says that you need to make n of the order of log of 1 over epsilon to get a good enough to get within epsilon. N has to be or log of 1 over epsilon. But with logarithmic 1 over log convergence, you need to make it exponential in epsilon, which is not very good, is it? So let's get back to this. So this is you compare with order 1 over n convergence for gradient descent. So if gradients exist and you use gradient descent for a convex function, so this is from lecture 7. It's much better than 1 over log n. It's exponentially better, right? So this is very slow. So can we actually improve this 1 over log n somehow? Okay. So there's been a lot of work recently on trying to improve convergence rates of subgradient algorithms because they are used so much in the context of machine learning. Okay, so but I'm not going to go over all that. So I'll talk maybe after the Thanksgiving break. We'll have 3 lectures, I think, and one of those lectures I'll devote to an interesting technique that can get you back to 1 over n type convergence. But okay, that's called a proximal gradient approach. But so that works in some special cases. But in general, you can still improve the convergence rate a little bit, at least. Actually, significantly improve by a different choice of alpha k. So anyone want to guess what I should make my alpha k? This alpha k is a little bit extreme, right? That summation of alpha k blows up, but summation of alpha k squared doesn't. So can we figure out a way to to make both of them blow up, but that the ratio goes to 0? Any guesses? Actually, I wrote that down right there, right? So that's, I already revealed it. So that's the 1 over square root of k. Actually, that turns out to be a better choice. So let's see what happens with 1 over square root of k. So in this case, the summation of alpha k squared is 1 over sum of 1 over k from 1 to n. And this can be shown to be less than log n plus 1. So you need an upper bound in this case to get an ordered result, because alpha k squared is going on in the numerator, right? So you need an upper bound on that. So here, since summation of alpha k was going in the denominator, a lower bound was good enough to upper bound the difference. Okay, so here we get that. As I mentioned, it's log n plus 1 is an upper bound on the summation of 1 over k. And if you look at summation of alpha k itself, that's 1 over square root of k. And 1 over square root of k, if you integrate 1 over square root of x, you get square root of x. So 1 over square root of k was also going to blow up to infinity, but at a different rate, at the rate square root of n. In fact, you can show that this is true, that it's lower bounded by 2 square root of n minus 2. So it blows up at the rate square root of n. So if you put these together, then the difference between xn star and f star is going as big O of log n from the numerator and the square root of n in the denominator. Okay, so this is better than 1 over log n. This is like 1 over square root of n, right? Okay, it's still worse than 1 over n, but than GD, right? But at least it's not as bad as 1 over log n. and it turns out that this is the kind of the best you can do. Any tweaks to this algorithm, any other choices of alpha k, none of that will help. Okay, so if you want a general result, this is the best you can do. 1 over n, 1 over square root of n is the best you can do. Maybe you can get rid of the log n, but 1 over square root of n is pretty much the best you can do for subgradient methods. Okay, but we'll see that in some special cases, by adding on another function into the optimization, and that's called proximal gradient, then if I take a function which has gradients and add that to a function that doesn't have gradients, right, then I can actually make the convergence rate go back to 1 over n. Okay, so that's one thing you could do in practice, that add some regularizer, what's called a regularizer, to make things work so that the convergence rate improves. Okay, any questions? So at the high level, what I want you to understand in the last 2 lectures was that you can actually apply gradient descent type methods even when you don't have gradients. Okay, as long as you can find these subgradients. Okay, but of course you lose something. You're going to lose something in the rate of convergence. Okay. Any questions? All right. Okay. So yeah, if you have any other questions about the homework, use Piazza. That has been quite active recently about homework 5. Otherwise, I'll see you guys on Tuesday when we'll do a review for the midterm, which the midterm is on Wednesday. Any questions about the midterm? No. And I'm going to give your next Thursday, I'm going to cancel that lecture for your midterm 2. So if you guys need to plan to go back, some of you are going back home, not coming back after Thanksgiving. If you want to go a little earlier, that's fine. There'll not be a class on Thursday. Okay. All right, everyone's quiet. Okay. All right, see you guys on Tuesday.